to thank you for having me to record. Okay, last talk is by Paolo Piazza from Sapienza University in Roma. And the talk has a title, Proper Action of Lie Groups, Cyclic Cohomology and Index Theory. Thank you.
Thank you, Katia. Thank you to the organizers for the invitation and for the opportunity to talk. I'm very honored to talk at this birthday conference for cyclic cohomology. So, and thank you for being to resist until the last talk. So here is the summary of my talk. So my talk connects directly to the one of Xian, and also a little bit with the talk of Gu Liang this morning. So it's in 4 parts, and you can read here the various topics. So let's start, and let me start with the geometric setup. So we have again a connected linear real reductively group. And we consider the Harish-Chandra-Schwarz algebra. And we know that this is a dense and holomorphically closed subalgebra of the Caesar algebra of G, the reduced Caesar algebra. And we are considering a co-compact G-proper manifold without boundary for the time being, and with a G-invariant Riemannian metric. We are also considering a Z2 graded G equivariant Dirac operator, and our goal is to extract some invariants out of this operator using cyclic cohomology. So remember that an important role in the theory is played by the smoothing G equivariant operators of G compact support. And remember also that we have the slice theorem that allows us to see X as an equivariant product of G and K-invariant submanifold S. Okay, so we shall write simply X as you see. And if you use this information, you can write the smoothing operators of G compact support as these projective tensor products. And we define, now we enlarge these smoothing operators of G compact support by replacing the functions on G of compact support with the Harish-Chandra algebra. Okay. And there are many different characterizations of these algebras, but I will not get into that. So for simplicity, from now on, I will not write vector bundles in the notation. Okay, so now what we have seen just now with Shang is a series of cocycles. So the first one was a cocycle that is defined taking the differentiable cohomology of G. Then remember that we also have the orbital integral. If G is a semi-simple element, the orbital integral is defined in this way. And then we know that this is a zero cocycle. It has the trace property. And finally, Song and Tang also defined for a cuspidal parabolic subgroup with Langdon decomposition MAN, another cyclic cocycle, a cyclic cohomology class that was denoted phi PG. So here G is a semi-simple element in N. of course, we know that we can also pass to the cyclic homology of the smoothing operators of G-compact support. Here is an example how from phi in the differential cohomology, you can define a cyclic cocycle in the space of, on the space of smoothing kernels. Here is the definition. This is classic. And C, as in the talk by Shang, this is a cutoff function for the action of G on the manifold. And similarly, we can pass from the orbital integral to a zero cocycle on AG's X, and in the same way, we can add the spatial variables to the cyclic cocycle of Song and Tang. Okay, so now a very important point, and this is a non-trivial point, is that these cocycles, they extend continuously to the Schwarz algebra. So they extend from the compactly supported group algebra to the Ari-Chandra algebra. And similarly, for the one defined on X, namely they extend from the smoothing operators of G-compact support to these more general smoothing operators on X. G invariant, of course, G equivalent. Okay, so this always takes some effort, but it is true that you can do that. Now, it is in fact a non-trivial result also that the Kohn-Moscovici projector, or at least what I call the Kohn-Moscovici projector, which is this projector, has entries in this algebra. Okay, so this is an analytic result that you need to establish. And there are actually several proofs of this you can use. At the end, it's something related to functional calculus and the Cauchy integral and so on. Now, that means that we can take this as a representative of a smooth index class, okay? Because I didn't say it, but these smoothing operators that you define using the Schwarz algebra are dense and holomorphically closed in the row Caesar algebra. Okay, so this is the Kohn-Moscovici projector is a smooth representative of the index class, and that means that we can pair this smooth index class with the cyclic cocycles that I had introduced before, and these are C-star higher, and we obtain C-star higher indices. Of course, we know from the fundamental paper by Kohn and Moscovici that there is a sharp difference between talking about indices in the compactly supported algebra and indices in a dense holomorphically closed subalgebra. These are the indices we are interested in, because then the index class has very important stability properties with respect, for example, to positive scalar curvature or homotopy invariance of the index class for the signature operator. Okay, so we really want to get to the Caesar algebra, the row Caesar algebra. So correspondingly, and this is basically part, a large part of the talk by Shang-Tang, is that there are correspondingly 3 index theorems, okay? And let me say that they have been all inspired heavily by the Kohn-Moscovici article on the Novikov conjecture. I mean, all the ingredients or the ideas are there, but of course, if you change your fundamental objects, you have to show other things, but the ideas are really there. Now, let me review these index theorems. So first of all, we have a theorem by Pflaum, Postum, and Tang, where they give a formula for the pairing of the index class with the cyclic cocycle defined by a group cocycle. So these are indices which are localized at the identity element. Then, so I don't review the formula because you just saw it. Then we have another index formula for the orbital integral. This is due to Peter Hawkes and Hang Wang. And so also these you saw basically implicitly in the talk by Shang. Here it is. And finally, we have the theorem by Hawkes, Song, and Tang, which gives a formula for the pairing of the index class with these cyclic cocycles, which have been defined by Song and Tang. Okay, so this index theorem you also saw 15 minutes ago, and really this theorem is obtained by reducing this pairing to a pairing on the quotient x over an. Okay, there is a delicate reduction procedure, but at the end you basically reduce this to a 0-degree index theorem. So basically an index theorem a la Hawkes-Wang, and then you apply the index theorem there. Okay, but the reduction is certainly non-trivial. So basically, this is my summary of part of Tang's talk. Now I would like to move on, and I would like to get to secondary invariants. And to talk about this, I want to first talk a little bit about Galois coverings, because Galois coverings are always the guiding ideas are always on Galois coverings. So let me talk about those. So we have a Galois gamma covering with the quotient x over gamma, and we take delocalized cyclic cohomology element of the group algebra. Okay. So as we know, Burgelia's theorem gives a decomposition of the cyclic cohomology of C gamma, and these are the constituents of this decomposition. So it's a decomposition in a direct product. Now, if the operator is invertible, and of course, if the operator is invertible, there is no index, the index class will be 0, then we can define higher row numbers under additional assumptions on the group gamma. So I already maybe talked about this in the non-commutative geometry seminar. This is a very delicate point, which kind of algebra you have to use in order to define these numbers. And there have been really a lot of work on these numbers, starting with Lot, then I did some work with Leichnam and Schick. Pushnik gave a very fundamental contribution in defining the right algebra for Gromov hyperbolic group. Higson Rowe, Xie Yu, Chen Wang, Xie Yu, Shegan, and also a paper of mine with Schick and Zenobi. They all treat these numbers and how you define them, basically, how what are the intricacies in defining these numbers. So these clearly are secondary invariants because they are defined when the operator is invertible, and in fact they are defined more generally when the index class is 0. So let me give an example. So if we take the delocalized trace, so Guo Liang already spoke about this morning, then this higher row number is nothing but the delocalized data invariant of Lot, which I define for you here. So D is always our operator, and we take this expression. And of course, there are delicate matters about convergence that you have to solve. And it is here that, for example, you assume that the conjugacy class is of polynomial growth, or the group is Gromov hyperbolic, and so on. Now, notice that if you take a manifold with boundary and such that the operator on the boundary is invertible, this allows you to define an index class, and by pairing a higher index. Okay. Now, even if you pair with a delocalized cocycle, in the case of manifolds with boundary, the higher index will be non-zero. This is a very crucial difference with the closed case, where the index class is always zero. If the index number associated to a delocalized cocycle is always zero. I mean, this really has to do with the fact that you can localize the parametrics in the closed case in a very close neighborhood of the diagonal, whereas you cannot do that on manifolds with boundary, either if you use Atiyah-Patodi single boundary conditions, or if you pass to the manifold with cylindrical ends. You always have a non-local parametrics, and this is why this higher index is non-zero, even if you take a delocalized cocycle. As a matter of fact, you have the following index formula, namely the delocalized index when alpha is a delocalized cocycle is equal to the higher row number of the boundary operator. Okay. And again, there have been many different proofs of this fundamental fact. For example, if you take the delocalized trace, then you recover this fundamental result, namely that this delocalized index is simply the lots delocalized eta invariant of the boundary operator. So now, why is this interesting? And the reason is the following, namely, in some geometric situations, this index class on the manifold with boundary will be zero. Okay, this happens, for example, if you have two metrics of positive scalar curvature, and the bordism between these two closed manifolds with positive scalar curvature, which supports a global metric of positive scalar curvature. Then the index class, of course, by Lichnerovich or generalization of it, will be zero. And then that means that the row number on one side, on one boundary, is equal to the row number on the other boundary. Okay, and this bordism invariance is extremely important because you know, we know that bordism is intimately connected with surgery. And so when you perform surgery, and this happens, for example, in differential topology or in positive scalar curvature metric theory, then you get a bordism, and if you have a bordism invariant, this is extremely important. And really, we have had many geometric applications of this principle that, you know, I cannot talk about here. It's just motivation, some of which you have seen this morning in Guoliang talk. Okay. Now, this brings me to the following question, namely, can we prove a higher delocalized APS index theorem on a G-proper manifold with boundary? Can we define higher row numbers in this way when we have an invertible operator? Are these higher row number interesting, as in the case of Galois coverings? Because, as I said, there are many purely geometric applications of these results. So the rest of the time, I will try to give an answer to these three questions. So first of all, let me give a short answer, namely just flashes. So for the cyclic cocycles coming from the differential cohomology of G, together with Hessel Postuma, we proved last year a higher APS index theorem. So this is not a delocalized index theorem because we know that these cocycles are concentrated at the identity element. And so these are not, will not produce delocalized, will not produce row invariants in the general sense. Now, if we take the delocalized, the zero cocycle defined by the orbital integral, then there is an APS index theorem that was proved last year by Peter Hawks, Heng Wang, and Beiling Wang. And finally, if we consider the cyclic cocycles defined by Song and Tang, then recently, also with Postuma, we proved a higher APS index theorem. Okay. So actually, this is a long paper, and where we in fact improve a little bit the results of Hawks, Wang, and Wang, and it also gives a different treatment of the theorem. Actually, in this paper, we prove a number of results, but I will not have time to report on them. Anyway, all these papers are in arXiv if you are interested. So let me get to the precise statements. So we take a G-proper manifold with boundary. All the structures are product type near the boundary. And we take a G-equivalent Dirac operator with an invertible boundary operator. Okay. Often we will consider the manifold with cylindrical ends associated to Y0. And well, first of all, because of the invertibility of the boundary operator, there is an index class which was defined by John Rowe in the K-theory of this sister algebra. So this sister algebra is obtained by considering operator of finite propagation, but the propagation is localized near Y0. Okay. Now, our goal is to extract numbers out of this index class and then prove index formulas. Okay, so this is the usual theme. And as I said, is a theme that has been around for many, many years. So first of all, let me try to clarify the existence of these higher indices. Okay. So first of all, there is a holomorphically closed subalgebra of this sister algebra considered by John Rowe. And as in the case of Kohn and Moscovici, there is a smooth representative of the index class. And as I will explain, this involves some pseudo-differential calculus. The three cyclic cocycles are well defined in the cyclic cohomology of this algebra. And so now we have the three higher APS indices simply obtained by pairing with the index class. So now let me skip, I hope Hessel will forgive me. Let me skip the index formula for the cocycles which are localized at identity elements. So this is a paper that will appear hopefully soon in Annals of K-theory. And instead, let me concentrate on these delocalized higher indices. And so let me begin with this index class. So this is the theorem. Assume that this is a L2 invertible operator. Then the delocalized data invariant is well defined, and this formula holds. So this is the same formula as in Hawks and Wang, but with this eta invariant entering into the picture. And as I said, this is proved by Hawks, Wang, and Wang, but we gave a different proof that I will talk about later. And also we improve on the hypothesis because they have to assume that G over the center is compact, whereas we don't have to assume that. Okay. Notice that it's a difficult result to show that the eta invariant is well defined. Here, the well-definedness of the eta invariant comes from the proof of the theorem. And it's only true if, it's only true here if we have a boundary operator, because we really use the proof of the theorem to assert the convergence of the integral, okay? Of course, this is not, from my point of view, a good, this is not good for geometric applications, because for geometric applications, for defining delocalized secondary invariants, you want to start from a closed manifold. So you don't want to start on a manifold, on the boundary of a manifold, okay? Then, of course, you will be interested in Bordism invariants, but at the beginning, you need a definition for closed manifold. And I must say that the next theorem, always by myself, Postuma, Song, and Tang, this took us a lot of time because the convergence, for example, near zero, it's a very delicate matter. And the convergence at infinity is not difficult if you assume L2 invertibility. But if you don't assume L2 invertibility, then it's a very delicate matter, and we had to use results by Moscovici-Stanton and by Bismuth. So if you want, the delocalized eta invariant in this context is defined under very general assumptions, okay? And this is in contrast, as Alain was saying, this is in contrast with the case of hyperbolic groups where you always have to put assumptions, on the operator and on the, you have to take the assumption that the group is Gromov hyperbolic or polynomial group. And here it works in general, of course, assuming G is a reductive real connected group. Very well. So now let me go to the other index formula. And the other index formula looks formally the same. Namely, we go to this quotient and we obtain this index formula, and it is proved in the same way. Namely, what we have to do, and analytically, this is much more complicated because you have the boundary you have to deal with, but basically the ideas are already in Hof's, Song, and Tang. So you reduce the theorem to this quotient manifold Y0 over AN, which is an M manifold, M proper manifold, to which you can apply the Hawks-Wang index theorem. So you pass from an M cyclic cocycle to a 0 cyclic cocycle, and then you can apply Hawks and Wang. Okay, this is the idea. Now, actually, it is an open problem whether there is a different description of this formula, and even in the closed case, a formula directly on Y0 by using some short-time behavior of the heat kernel. We don't know that. That seems to be a very hard question, in fact. So now that we have these theorems, we can define row numbers. How do we do that? So now we take a manifold without boundary, okay? And we take an equivariant spin structure, and we assume that we have a metric of a G-invariant metric of positive scalar curvature, and then we can define the row invariant of this metric as the delocalized eta invariant of the corresponding spin Dirac operator. Similarly, we can define this higher row invariant associated to a cuspidal parabolic subgroup. And now here comes a very delicate point. Let me go back one moment. you see, in the case of free actions, you didn't have any contribution from the interior. Here you have this ATIA bot type contribution. And so it would seem that this is not a Bordism invariant. The thing that I just defined is not a Bordism invariant. But if G does not have fixed points, and this happens, for example, if G is a non-elliptic element, namely is not conjugated to a compact group, then the local part is not there, and then these are invariants for equivariant concordance or equivariant positive scalar curvature Bordism, okay? And so now you can hope, but this is only a hope, there is a lot of work to be done, that you can use the usual techniques in order to look at the space of positive scalar curvature metrics on a G proper manifolds, okay? But let me, and similarly, you can look at G equivariant homotopy equivalence, but there is a lot to be done in this direction, and the reason is the following. So all the results that have been proved, Weinberger U, Shie U, myself with Schick and Zenobi, they all use surgery in a very crucial way. Now here you would have to do equivariant surgery, and the equivariant surgery is a well-developed subject when G is a compact group, but is basically nothing has been done when G is acting properly on your manifold. So there is a lot to be done here, and these are very difficult subjects that needs to be developed somehow. We haven't done that, I will tell you. Now, I now want to give just a few ideas how you prove these theorems. I will try to finish on time also because I'm the last talk of the day. So everything, our techniques go back to some work I've done with Hitoshi Moriyoshi and also with Sasha Gorokowski. And that was also explored in a different context by Lesch, Moscovici, and Flaum, namely the interplay between relative K-theory and relative cyclic homology, and say absolute K-theory and absolute cyclic homology. So let me explain this point. So now, as I said, I look at the manifold with cylindrical ends associated to my manifold with boundary. Now, forget about the group for a moment and take just the compact case. So our metric is like that, and sorry. Full screen, yes, sorry. So notice that the volume form is of that type near the boundary. So there is a singularity near the boundary. And now we look at the B pseudo differential calculus. This is obtained by looking at blown up space, and so let me say, sorry, I have to take out. Could you please tell me whether you are hearing me? Because I have a Katya.
Yes,
we can hear you.
Okay, sorry. No, I had the doubt that I was talking to the void set. Thank you. So the B calculus is obtained by looking at kernels on this blown up space. So I only explain the figure. And so what happens is that you have introduced a new boundary phase in the product of your manifold Y with itself. And when you restrict your operators on this boundary phase, the geometric structure of this new boundary phase is such that when you restrict kernels to this new boundary phase, you obtain a translation invariant operator on the cylinder. And this defines the so-called indicial homomorphism. So you go from your manifold Y to the cylinder translation invariant operators, pseudo differential of some sort. Okay. Now, when you look at elements of order minus infinity, then the elements which are in the kernel of the initial homomorphism, clearly, let me go back. So I didn't tell you that they are 0 on this left boundary and on this right boundary. Now, if you assume that the initial operator is 0, they are also 0 on the new boundary phase. So they are 0 on all the boundary phases of this manifold with corners. And that means that these operators are compact in L2 because they are 0 at infinity. Okay. And so the kernel of the initial homomorphism is denoted that way because it's really like smoothing operators on a closed manifold. In fact, you have a short exact sequence of algebras. And let me point out that when you take a symbolic parametrics, then the reminders will not be vanishing on this new phase. So will not be compacted. This will not be a true parametrics. But what happens is that if the operator is invertible, then you can improve this parametrics and get a reminder that is in the smaller algebra of operators with zero boundary values on all the boundary phases. So this is a true parametrics. So for example, you can do that for the parametrics that enters into the definition of the Kohn-Moscovici projector. You take this parametrics. It's not good because the reminder is the heat kernel, which has a non-trivial initial operator. The initial operator is the heat kernel on the cylinder, so non-zero clearly. But you can change it. You can remove the Taylor series at the new boundary phase and produce a new parametrics. Okay. Now, let's go back to G-proper manifolds. Using the slice theorem, we can define a short exact sequence of algebras. And for example, just as we did before, the central algebra is just the projective tensor product that you see in this line, okay, where we use the B pseudo differential operator on the slice. So this is a heavy notation, so let me use this shorter notation. So this short exact sequence will play a fundamental role because we will be talking about relative classes. So now one result, which is purely analytic and that takes quite a lot of work, is the following. So this algebra that I just introduced is a dense holomorphically closed subalgebra. So this is the subalgebra I was talking about before. The Kohn-Moscovici projector is an element in this algebra, in the unitalization of this algebra. This is actually a very non-trivial result. Similarly for the one on the cylinder. Now, if the operator is invertible on the boundary, then we can use this famous improved Kohn-Moscovici projector and define a smooth index class. Another purely analytical result is that the cylindrical class converge to this matrix as S goes to plus infinity. I mean, if the operator on the boundary is invertible. Now, that means that this triple, the Kohn-Moscovici projector, E1, and this path of projectors in the cylinder, they define a relative index class. And the important point is that these two index classes correspond under excision. This is a very important point. Very good. Now, I'm almost done. So let us go back for a moment to compact B-manifold, then, as I said, the smoothing operators are not trace class in general. And so Melrose has defined a regularized trace, the so-called B trace. Unfortunately, the B is very bad in a talk in cyclic cohomology because it's also the differential, but I'm sure you will understand. So this is defined basically by subtracting the logarithmic divergence in the integral over y. And the Melrose formula, so this is not a trace, even if it is called a trace, is not a trace, but there is a very precise formula for the B trace of a commutator. So here, remember, IR was the initial operator, translation invariant, and so we can take the Fourier transform of this operator. And this is the expression for the B trace of a commutator. So now let us go back to a G proper manifold YH, and let us take those famous 3 cyclic cocycles. And now, instead of taking integrals, we take B integrals. And if we take B integrals, we can extend these functionals from the small algebras to the big algebra. For example, we can do that for the orbital integral. And then in that way, we obtain a functional, but of course, this functional will not have the B differential equal to 0 because it's not a trace, okay? But we can use Melrose formula to compute this differential. And here is the formula, I mean, is the formula we know. So now, if we consider this one cochain, what you can prove, and here again, there is some analysis involved because you have to show that everything extends to the Schwartz algebra of Harish-Chandra and so on. You can show that this pair is a relative 0 cocycle. And the most important information is this formula. Namely, the left-hand side is what you want to compute, and the right-hand side is what comes from these relative classes. Now, if you unwind the relative pairing on the right-hand side, and you do some computations, then for each s greater than 0, you have this equality. And now you have to do a very careful study of the heat kernel for small s in order to take the limit as s goes to 0, okay? And the index formula I was talking about is obtained precisely by taking this limit as s goes to 0. And the higher case is definitely more complicated, but the idea is the same. The idea is the same, and the technicalities enter, for example, when you have to show continuity, but the ideas are exactly the same. And so I think I'm maybe 2 minutes early, or maybe even 5, but I think this is a good point to stop. And so I thank you all for that, for your attention.